let's go over some questions. An old, slow car moves at a steady 10 kilometers per hour on a straight highway, while another car zooms past at a steady 120 kilometers per hour. Which car has the greater net force on it? Right, let me give you a hint first. I've said this before. Whenever you read a question like this, you want to underline or circle it or something, the important words. And in my opinion, what's important? Steady, straight, steady. All right. So pause your video and figure it out. Okay, so here we go. So the old slow car, so you can see they're trying to trick you, right? Old slow car, you know? An old slow car, steady speed, straight highway. So that means that the velocity is constant, so the acceleration is 0, so the force on it is 0. Then the other car zooms past, right? So you think, whoa, it zooms past, has a big force on it, but what does it say? What's the important word? Steady. And you're assuming it's going straight, and it doesn't say that, but you have to assume that. So the speed is steady, we're assuming the direction is steady, so that means the velocity is constant, that means that the acceleration is 0. So that means that the net force is 0. So the net force is 0 on both of them. Right? So as soon as you see that steady and straight, you say, haha, nothing is changing, right? Nothing is changing. So they have no net force on them. All right. Okay, this is. Now we want to talk about something called an inertial reference frame. Okay, you're a passenger in a car and you're not wearing a seatbelt. Without increasing or decreasing its speed, the car makes a sharp left turn and you find yourself colliding, with the right-hand door. Which is the correct analysis of this situation? Now hold it. What's correct mean? Correct means from the perspective of an inertial reference frame. We've talked about this before. Just to remind you, what does that mean? Inertial reference frame. It means a reference frame that is not accelerating. Okay? So, you're in a car, right? And all of a sudden, a quick left turn, right? Well, come on. You're making a turn. You are not an inertial reference frame because you're accelerating. Your direction is changing. So what would be the perspective from an inertial reference frame? Well, let's say there was a drone up there in the air, and it's just staying at the same location, right? So the drone's reference frame would be an inertial reference frame because nothing is accelerating. All right, so read it, figure it out. Okay, so what would the drone see? Oops, that's the answer. Starting at the time of the collision, the door exerts a leftward force on you. Why is that? Well, think about it. Here's you, right? Newton's laws say you're going to go straight unless there's a force acting on you. So without any force, you're just going to keep going straight. But all of a sudden, you take a left. Well, why do you take a left? Because there has to be a force acting on you to make you go left, right? Well, what is the only force? The door acting on you. Okay? So in other words, you tried to keep moving straight, but the door pushed you to the left. So the door provides the center or left directed force that makes you move in a circle. Okay? So this is a real big deal. Whenever you analyze a situation, you always want to analyze it from the perspective of an inertial reference frame, like the drone that's at the same location, right? When you're in an accelerating reference frame, you can't use Newton's laws. So we don't want to do that, right? Always analyze things from an inertial reference frame, not accelerating. Okay, all right, so let's be picky now. Is Earth an inertial reference frame? Remember, the definition of an inertial reference frame is not accelerating. Is Earth in an inertial reference frame? Absolutely not. I mean, come on. It's spinning, right? Then it's orbiting the sun, and our solar system is orbiting other locations. I mean, not even, it's not, right? It's not an inertial reference frame. However, it's close to an inertial reference frame. So for most of the problems that we do, we're going to assume that Earth is an inertial reference frame. You should really read the book. There's a nice little section that discusses the fact that it's not an inertial reference frame and what does that result in. It's kind of interesting. Okay, let's just quickly review. A force is an interaction between two or more objects. Two, right? Two more objects. Newton's first law, an object at rest remains at rest. Object that's moving will continue to move in a straight line, constant speed, if the net force on it is 0. Okay, F equals ma, you know, A equals dv dt, and the whole thing was a normal force. All right, here's a question for you. You push your 2 kilogram book along a tabletop, pushing it with a 10 Newton force. But there's also a 4 Newton frictional force. We haven't even talked about friction yet, but that's okay, you can figure it out. The book's acceleration is what? So pause your video and figure it out. Okay, remember, when we write F, we're being lazy. It really means the net, or the sum of the external forces. So here, you know, so I mean, we really should do that, but we're just too lazy. We never bother. Okay, so you push a book this way with 10 newtons, but what does friction do? Does friction help or hurt? I mean, is friction pushing it along that way? Of course not. Friction is the opposite direction. So the net force, you have 10 newtons in the direction of the push, but then you have minus 4 newtons because friction opposes the motion, right? And the mass is 2 kilograms. And so the net force is 6 newtons. The mass is 2 kilograms. What's a newton? It's a kilogram times a meter per second squared. And then you have the 2 kilograms. So 6 over 2 is 3. So we have 3 kilograms cancel. So you get 3 meters per second squared. Okay, another one. The main point of Newton's law of motion is that forces cause what? F equals ma. What does a force cause? So vote. Pause your video and vote. Okay, acceleration, right? Or you can say change of motion, but that wasn't one of them. Okay, all right. An elevator is going up at a steady speed. So again, if this were on a test, and if it were me, as soon as I see that word steady, I'd circle it or underline it or something like that, because that's super important. And you can, you know, if it's an elevator, you know the direction is not changing, right? This is a weird elevator. Okay, an elevator is going up at a steady speed. Identify the forces acting on the elevator. Now notice it says forces, so there's probably more than one correct answer. So please pause your video and figure it out. Okay, so this is really, you know, this is like the precursor to drawing these force diagrams. You have to first identify what the object is, which is sort of obvious, it's the elevator. And then you have to identify the forces acting on the object. So what are the forces acting on it? Well, there's something pulling it up, so that's tension, right? That's tension. Earth is pulling down on it. Earth always pulls down on things that have a mass, so there's the weight. Now what is this? The force of motion. What is that? I don't know. It's ridiculous. There is no such thing, all right? There's no such thing. The force of motion, I don't know what that is. And the inertia of the elevator, that's not a force. So we don't care, you know? The question says, what are the forces acting on the elevator, you know? I mean, what did it say? The color black. What if the elevator's black? Is that a force? No, so we don't care, right? The inertia is not a force. We don't care. Okay? All right, so the answer is just 1 and 2. Those are the only forces acting on it. So if we were to draw it, the force diagram, here's the elevator. Here's the weight. Weight. If you want, you can say mg. And then tension, uppercase T. And if it's steady speed, that means that this magnitude has to be the same as that magnitude. So if I were really, really careful, I would make this length equal to that length. That's pretty close, right? All right, because if the forces are steady speed means A equals 0, so that means that the sum of the forces equals 0. Right? All right, one more. Sometimes give it away. Is the tension greater than, equal to, or less than the weight? Well, I just gave it away, right? As soon as you see steady speed, you say acceleration is 0, so the net force is 0, so the tension has to have the same magnitude as the weight, right? So what's the answer? So is the tension greater than, equal to, or less than the weight? It's equal to. We just said that. Equal to, right? Because the forces cancel, so the acceleration is 0. All right. Now, so this is what you're supposed to do. All right? You are supposed to answer all these questions, and I mean, if we were in a classroom situation, you would answer the questions and you would discuss them with your neighbor, and it would be wonderful, but we can't do that now, so, oh well. All right, so let me just explain what you're doing. So here's a table, or what I'm doing is, here's a table, and here's a box, and so I'm pushing it, so there's a force, me, or could be you, I don't really care, right? And the box moves, right? So there's the velocity, and it's steady. Okay? So I'm pushing a box along a table, and a steady speed. All right? All right, so pause your videos, please do that. Don't just watch me. Pause your videos and answer every one of the questions. It's going to take a while, but it's all right. All right, so pause your videos and do it. All right, so let's answer the questions. So the box is moving with a steady speed. Okay, number one, I'm exerting a force on the box, so why isn't it accelerating? Well, if it's going at a steady speed, the acceleration is 0. If the acceleration is 0, the net force is 0. So my force is this way, but what's another force? Well, friction, right? Friction opposes the motion. So if the box is not accelerating, because the frictional force is equal and opposite to my force. Number two, what are the forces on the box? Draw a force diagram. So again, this is the key to the entire chapter. You have to be able to do this. Okay, so we want every single force. There's my coordinate axes. Okay, so the box has a mass. So you're always going to do this. So there's the box. So one of the forces is the weight. Weight. And you don't have to write equals mg. I'm just doing it. Okay. There's also a normal force, right? There's no acceleration along the vertical, so there has to be, if there's a weight, there has to be an opposite normal force, right? So there's a normal force. Okay, I'm pushing on it. Let's say I'm pushing this way. So there's like F me. Oops, that's not F. And then there's a frictional force. I'll just say it's friction. Okay. And again, if I were super careful, which I guess I'm not. If I were super careful, there's no vertical acceleration, so this magnitude has to be the same as that magnitude. There's no horizontal acceleration, So this magnitude has to equal that magnitude. So the net force is 0 in both directions. All right? So I just did 1, 2, 3, and 4. Right? So that's a force diagram. We talked about the magnitude, so forth and so on. Okay, now what I want to do is this. So now what I'm doing is here's the table, and here's the box. So I'm going to push it and then let go. So I give it a push and then I let go. So what happens? You know? So after I let go, it goes slower and slower and slower, then it stops, right? Okay. All right. So answer the questions. All right. Oh, let me show you. Hold on. Yeah. Okay. So pause your video. Answer the questions. Okay, let's talk about it. All right, so you push on the box, you let go, the box, keeps moving, but it slows down and it stops. All right, number 1, after I am no longer touching the box, and before it stops moving, what are the forces? Well, I'm no longer touching it, right? But there's still weight, there's still normal, there's still friction. The only force that's missing is me. So, there's the weight. There's the normal. Now remember, this was my direction, so the friction is this way. So force of friction. And the velocity, remember the velocity is this way. Okay, so there's a force diagram. Compare the magnitude of the vertical. There's no acceleration along the vertical, so that magnitude equals that magnitude. Okay, in what direction does the velocity vector point? The way it's moving, right? Right? In what direction does the acceleration vector point? That's a good question. Well, there's only one horizontal force, right? And so therefore, F equals ma, so the acceleration is that direction. Now this is cool. This is a good review from our earlier chapter. The velocity is that direction. The acceleration is that direction. What did we learn a long time ago? When acceleration and the velocity have opposite directions, the object slows down. Isn't the object going to slow down once I let go? Well, yeah! So it all makes sense, right? It all makes sense. All right. Oh, let's see. Is that number 3? Yep, sure is. Okay. So a student moves a box of books by attaching a rope to the box, pulling with a force of 90 newtons at an angle of 30 degrees with respect to the floor. The box of books has a mass of 20 kilograms, a force of friction 75.5 newtons. Find the acceleration of the box. Okay, so this is what I was talking about at the beginning of the chapter. All I want you to do now is draw the force diagrams. We're going to solve the problem in a future chapter. So, or me, get a piece of paper, draw the force diagram, then leave a big space so you can solve it and use the same force diagram but solve it in a future chapter. So pause your video and do what it says. Okay, let's do it. All right, so the first question you have to answer always is what are the forces acting on the object, Well, first of all, what's the object? So, it's easy, right? For this problem, it's easy. The object is obviously the box of books. Sometimes it's not going to be so easy. But that's the first question, what's the object? Second question, what are the forces? Well, you know, there's going to be weight, there's going to be the normal, there's going to be friction, and what else? The rope, the tension. Anything else? No? All right, so here you go. All right, so the weight is always down towards the center. Oh, let me do it. The weight is always down towards the center of the earth. So let's do that. There's the weight, mg, right? There's going to be a normal. I'm not going to make it the same magnitude, you'll see why in a minute. Right? Friction opposes the motion. I'm not going to write friction all the time, but we'll get to that later. And then there's going to be some kind of a tension, right? Tension. And all right. So that's the 90. That's the 90 newtons. Okay. And it's going to accelerate this way, right? So that's it. Okay, that's it. Now something that's kind of important. It's not accelerating this way, right? So the net force in this way has to be 0. So, we can resolve this tension into a component this way and this way. And if it's accelerating this way, this has to be longer than that, so I got that right. And there's no acceleration this way, so this plus this should equal that. I did a pretty good job, right? Close enough, right? So no acceleration this way, acceleration that way. That bigger than that, this plus this equals that. Okay, for my grade. All right? Same thing. Don't worry about this K. That's the friction. We'll get to that in a little bit. So the acceleration is that way. The net force is that way, right? So there you go. You have to understand this. Trust me. You have to understand this. Okay. Is that number 3, huh? Okay, you didn't see that? All right. Now, we've been talking about friction. Well, let's learn about it. We're going to be using it the rest of the semester, so let's learn about friction. Okay, friction. All right, let's see where it is. Okay. All right. So let's say I'm pushing this against the wall, but I'm not pressing very hard, so the thing just falls, right? So the friction's not very big. On the other hand, let's say I push harder. Well, now the friction has increased, so it's not going to fall. Agreed? All right. So, what are the forces? What are the forces involved? Well, let's do what we always do. Draw the force diagram. Okay, so what are the forces? So it's kind of, it's best, I was pushing it like this, right? So just kind of pretend there's a hole in the wall. I can put my head here. I can kind of see what was going on from the side, right? But anyway, let's do it. So obviously there's weight. It's always weight. If the object has mass, there's weight, right? So weight. Now, I was pushing this way, right? So let's just say that it's this way. Okay? So that's the push, the force of the push. Okay? Now, look at, if I'm pushing this way and the object is not accelerating this way, that means that why not? Because there's the object in the way which is exerting a normal force, right? I mean, if this were tissue paper, that thing would accelerate. So again, I'm pushing the eraser in, this way, and it's not accelerating in that direction, so that's because the whiteboard is exerting a normal force that way. Okay, so again, let's say that this push is that way, so there has to be a normal force, same magnitude. All right, so that's the normal. That's the normal force. Now, what's up? What's the up force? The friction force, right? Because Again, if I just barely touch it, there's not enough friction. But if I push it hard, there's enough friction. So in other words, this is the direction of motion, down. So friction is always opposing motion. So friction is this way. Friction. Okay. All right. Now, that makes sense. But notice, again, if I push really hard, there's a lot of friction that's not going to fall. If I just barely touch it, with, I don't have a lot of friction, it's going to fall. So what does the frictional force depend on? Well, you could say how hard I'm pushing on it. Okay, but what's that equal to? That's equal to the normal force, right? Right. So, either way, however you want to look at it, it's equivalent to saying that the frictional force is proportional to the normal force. Okay? The frictional force is proportional to the normal force. Now, let's say that pretend this is an ice cube, and pretend this is a big chunk of ice. You think that compare that to this being sandpaper, and this being sandpaper. Do you think there'd be a difference in the frictional force? Well, of course there would, right? So, so this is true, right? The frictional force is proportional to the normal force, but it also depends on the properties of the surfaces, the surfaces. So, so what we can say then is that the frictional force is equal to a constant, which has to do with the properties of the surface, times the normal force. Okay? So that's an important equation, but it's not the end of the story yet. Now, actually, there's two kinds, we're going to talk about three kinds of frictional force. What we're demonstrating here, is the static frictional force. Okay, what's static mean? Not moving. Okay? So what I'm going to demonstrate is that the static frictional force is less than or equal to, this is called the coefficient of friction. It has to do with the properties of the surface times the normal. Okay, so let's talk about that. Okay, let's talk about that. Wait a minute. Okay, so you need to see this and see this. That's good? All right. All right. So what I want to do is explain this equation. The static frictional force is less than or equal to mu n. Okay, basically I'm going to talk about why there's a less than sign. And again, static means not moving. All right, ready? And I'm just going to make up numbers and exaggerate and all that kind of stuff. So here's a heavy box on this card. Okay? So I'm going to exert a force on it. Ready? Here we go. All right. So I just pretend I exerted a force of 0.01 newtons. Kind of small, right? Okay. Well, I exerted a force on it, but did it accelerate? No. Why didn't it accelerate? Because there was a frictional force, right? And what was the frictional force? I mean, think about it. F. Okay, here. The sum of the forces equals ma. Well, what's the sum of the forces? What's the sum of the forces? The sum of the forces is me, right, plus friction. And that has to be 0. So the force of me was equal and opposite to the force of friction. All right? So if I blew on it with 0.01 newtons, what's the force of static friction? 0.01 newtons. All right, so the friction was kind of small, right? Okay, now watch. Right? So now I blew hard. So now I blew on it with 0.1 newtons. Well, did it accelerate? No. So therefore, what has to be the force of friction? 0.1 newtons. Because the net force is 0. Because the acceleration is 0. So 0.1 newtons. Okay. Now I'm starting to get frustrated because this dumb thing's not moving. So now I'm going to use my pinky power, right? So, okay, so I exert a force of 1 Newton, right? 1 Newton. Did it accelerate? No. What's the net force? 0. So it has to be the static frictional force. 1 Newton. So look at it. We started off with 0.01, then it went to 0.1, now it's at 1, right? But it's still not moving, so these are still static frictional forces. Okay, I want this box to move. So now I'm going to push it with my hand. Man, it still doesn't move. All right, so I exerted a force of 5 newtons on the silly thing. Didn't move, didn't accelerate. So the frictional force, net force is 0. So the frictional force has to be 5 newtons. Right? Okay, now, come on. I gotta get this thing to move. Gotta get this thing to move. So now what I'm gonna do, I'm gonna push it with my 5 Newton force. I'm gonna give that little blow. Wow, it moves. Okay? All right, so this was I'm gonna say this was the maximum, Fs max. All right, that's the maximum static frictional force. When I exceeded that Fs max, 5 newtons, it moved. So it's no longer a static frictional force, it's a kinetic frictional force. All right, so now you can see, right? Fs is less than or equal to mu n. Right, so this is what we say. We say Fs max equals mu n. But Fs is less than or equal to Fs max, right? Right? And we saw that. Here the friction was less than the max, right? And then once you exceed the static friction, when you exceed the static friction, it's moving, so then it becomes kinetic friction. Okay, let's quit.